Algebra Unit 5, Lesson 12, Notes 12, Least Squares Regression Lines. When lines of best fit are drawn by hand, many different lines could be drawn. To avoid this, a calculator can be used to determine the actual line of best fit, also called the least squares regression line. Kendra likes to watch crime scene investigation shows on television. She watched a show where investigators used a shoe print to help identify a suspect in a case. She questioned how possible it is to predict someone's height from his shoe print. To investigate, she collected data on shoe length in inches and height in inches from 10 adult men. Her results are shown in the table and scatter plot below. Okay, so normally we would say find a line of best fit, draw it in, and find the equation. But as you realize, we would have different lines depending on who drew them. There is a way to do it on your calculator. The directions are below, and I'm going to walk you through them step by step. So make sure you have your TI-84 calculator ready. So the first thing we're going to do is we're going to make sure our diagnostics are on. They might be on because you had them in a previous lesson. Hopefully they are. If not, just a refresher, hit the second button and the key 0. Above it says catalog, which will bring you to this screen. You can go ahead if you want and hit the D button on your calculator to bring you down to the D's. Otherwise, scroll down until you get to diagnostic on. Hit enter and enter again so it says done. It's always a good idea when you're doing anything with statistics to make sure your diagnostics are on. And again, they may already be on, but just in case. Okay, so here's what we're going to do to find our linear regression line. You're going to hit that stat button, which is near your arrow pad, just to the left of your arrow pad, below the delete key. You are then going to hit enter or edit, which will bring you to a blank list screen. From there, you're going to enter your X values or your shoe length in your list 1. So go ahead and do that. Pause if you need to. And then in list 2, you're going to enter your height. So they should match up. You should have 10 of each. Again, pause so you can catch up. Okay, once you have your values typed in, you're then going to hit that stat button again, which will bring you to this first screen. Arrow over to the right to hit calc. Make sure calc is highlighted in black. And then you actually want linear regression. Notice how it has ax plus b. Similarly, mx plus b we've learned, okay? It's the same thing. There is another one down here. It just reverses what a and b stand for. It doesn't matter. I like to use this one because I like everything in slope-intercept form. Go ahead and hit enter, which will bring you to this screen. Your X list is in L1 and your Y list is in L2. Go all the way down, arrow down to calculate, and hit enter. You will come across this. It gives you that equation again, y equals ax plus b, which is slope-intercept form. It tells you a, or the slope, and it tells you b, or the y-intercept. The r and r squared we're going to talk about a little bit later in the unit. So we want to do, I believe we want to find it to the nearest thousandth, if I remember correctly on your paper. So we want to write it out as y equals 3.657x plus 25.27 round up to 7. Okay, so keep this screen open. I'm going to go ahead and go to the next slide so we can jot down this information. Okay, first of all, it asks us, does there appear to be a relationship between shoe length and height? If so, describe it. Well, if you could just look at the scatter plot for this. On the scatter plot, it does seem to be increasing, not very strong, so we would say it is a weak positive correlation. Positive because it's increasing. So weak positive correlation. Okay. Over to the right here, use the calculator to find the linear regression equation. So again, look back on your calculator. Remember, it's in y equals ax plus b. to the nearest thousandth, y equals, our a value to the nearest thousandth was 3.657x plus our b value to the nearest thousandth was 25.277. Remember, we had to round up that value at the end. And if you do this on your calculator, everybody will get the same exact linear regression. It calculates it for you. That's the beauty of it. Provide an interpretation of the slope of the least squares line. Well, the slope is 3.657, and this is referring to the change in height versus the change in shoe length. So let's go ahead and jot that down. I'm going to start typing here. The change of height versus the change in shoe size is about, and again our slope is 3.657. Oops. That's all you have to say about the slope. Using your equation, predict the height of a man with a shoe length of 12 inches. Remember, our shoe length is our x-axis. You could look right up at your scatter plot or at your chart. It tells you that x equals shoe length. So all we're going to do here is plug in 12 for our shoe length. So using the equation above, I always like to rewrite it down. 3.657x plus 25.277. We're going to plug in 12 where x is. You can jot that whole thing in your calculator. When you jot that in, you get y equals 69.161 inches. I want you to try letter B by yourself just to get a feel for the calculator and then answer the questions that follow. Let's take a look at letter C. Below is a scatter plot of full birth weight and mare's birth weight. The equation of the least squares line is y equals negative 19.6 plus 2.48x. It gives us our linear regression equation, or our line of best fit equation. Therefore, we don't have to do anything in the calculator. What full birth weight would you predict for a mare who weighs 520 kilograms? If we look over at our table, our mare weight is on the x-axis, and our full weight is on the y-axis. So if we are looking at a mare weight of 520, that refers to an x value. So we're going to go ahead and plug in 520 in for x in our equation. Y equals negative 19.6 plus 0.248 times 520. Plug that into your calculator, and you would get 109.36 kilograms. How would you interpret the value of the slope for the least squares line? We have that the full birth weight versus the mare weight we can say increases by, and our slope here was 0.248. So this is an interesting question here. Does it make sense to interpret the value of the y-intercept in this context? Explain why or why not. Well, our y-intercept, if we look up at our equation, our y-intercept is negative 19.6. Remember, we're talking about full weight versus mare weight, okay? So when we do this, the y-intercept would be the y value, which is our full birth weight, which is negative 19.6. You can't have a foal that is born at a negative weight. It just doesn't make sense. Okay, so let's jot that down in a proper explanation here. So does it make sense to interpret it? I would say no, because that would imply that the mare birth weight would be 0 and the full birth weight would be negative 19.6, which simply couldn't happen. So why is it called a least squares line? Let's return to Kendra's shoe length and height problem. Use the regression equation y equals 3.66x plus 25.28 to find the predicted heights for each shoe length. Some of them are already done for you. So the ones that we're missing are right here. We have no predicted value for a shoe length of 11.6, 11.4, and 12.8. So off to the side somewhere, let's go ahead and plug those values in for x. Oops. Okay, so our first value is 11.6. Y equals 3.66 times 11.6 plus 25.28. Plug it into your calculator. We get a value of 67.736. Fill it in your chart. Our next value is 11.4. 3.66 times 11.4 plus 25.28. When we plug that in, we get 67.004. And write that in the chart. And lastly, let's plug in 12.8. Y equals 3.66 times 12.8 plus 25.28. Plug it in, and we get 72.128. Okay. Now on the right-hand side here, it says to calculate a prediction error, subtract the predicted value from the actual. This prediction error is called a residual. Calculate the remaining residuals in the table above. So again, actual minus predicted. So we only have 3 blanks here. Here's our actual height, it tells us above, and here's our predicted. So on your calculator, 67 minus 67.736. And when we do that, we end up with a negative 0.736. For our 11.4 value, we have 68 minus 67.004, and we get 0.996. And for our last value, 12.8, we have an actual of 70 and a predicted as 72.128. Subtract those, and we get negative 2.128. Okay. Explain why some of the residuals are positive while others are negative. Well, if you look at your actual, you're doing a subtraction problem. Your actual minus the predicted. So if your predicted value happens to be larger than the actual value, you're going to get a negative result, and vice versa. So let's go ahead and jot that down. If the predicted value is larger than the actual, it's negative. Well, we'll say the residual is negative. Similarly, if the predicted value is smaller than the actual value, the residual is positive. If overall the residuals tend to be small for a data set, what does it say about the fit of the line to the data? Well, we want the residuals small. If the residuals are smaller, it means that they're closer to the line, the residual line, and therefore would be a good fit. So the points would be close to the line, and therefore a good fit. Find the sum of the residuals. Notice that the value is close to 0. Why does this happen? So what we're going to do, we're going to do it on our calculator, make things simple. We're going to total up all of these residuals. So on your calculator, 2.604 plus negative 3.468 plus 1.068, and so on. Take a moment, plug those in. When you add them up, we end up getting negative 0.392, which is not 0, but it's pretty close to 0. So why does this happen? Well, remember, we get negative and positive residuals. So this happens because the negative and positive values balance each other out. Since the signs of the residuals offset each other, statisticians find it more useful to square the residuals. Therefore, the line that has the smallest sum of squared residuals is called the least squares line, or the best fit line. Calculate the remaining squared residuals to the nearest 10,000th, then find the sum of the squared residuals for Kendra's data to the nearest 100th. So up here, square of residuals, all that we're doing is we take this value, 2.604, and square it. Remember, there is that x squared button on your calculator, diagonal from the 7 key. So make sure this is in parentheses, negative 0.736. Hit that x squared button, or you could also hit the caret 2. And when you do that, you get a result, and we want it to the nearest 10,000th this time, as in the directions, 0.5417. Generally, I always round to everything else in the table. So this whole square of residual column, it looks like they're all rounded to the nearest 10,000th, so that's what I would round to. All right, when we do our blue value here, 0.996, and we square that, we get 0.9920. And when we square this last value, we get 4.5284. Remember to put that residual in parentheses. When we your calculator, we have to force that operation so that we get a positive square of residual. Then what I want you to do is add all the squares of the residuals together. Now, they're all positive this time, so you will not get an answer close to 0. Okay, this isn't looking for any sort of explanation. It just wants us to add them up. When we add them up, we get 34.5235 to the nearest 100th, 34.5235.